Hello, everybody. This paper is about spinning light clocks. Uh, the title of the paper is Spinning Light Clocks Review Time Contraction in Spinning Non-Inertial Frame. My name is Tao, and my nickname is Light Clock. You can call me Light Clock also. Here we introduce some basic concepts. The first one is time dilation, which means time goes more slowly. The second one is time contraction, which means time goes more quickly. And the third one is light clock. It is a conceptual clock composed of two mirrors and a light signal. One tick of the clock corresponds to the process in which the light signal initially leaves one of the two mirrors and then reaches the other mirror and then returns to the mirror it initially leaves. And the fourth one is light bending, which means the phenomena of the curved trajectory of the light ray. In the current physics books on Einstein Relativity, it is mentioned that time dilation happens in moving frame. Here, it will be shown that time contraction is also possible in moving frame, and this is demonstrated by spinning light clocks. This is the abstract of this paper. Spinning light clocks are invented, and their behaviors are investigated. For a spinning light clock, the two mirrors rotate around a common point between the two mirrors, and the two mirrors are mathematically abstracted as 2 points. The trajectory of the light ray in the spinning frame is plotted, and it is curved. This means light bending appears. The formula to calculate the time interval for the light ray to travel from one mirror to the other mirror in the spinning frame is given, and it is found that time contraction happens in the spinning frame. Here it shows a stationary light clock. The photon bounces up and down between the two stationary mirrors. The green color disk represents the photon. The blue line segment represents the light trajectory, also the photon trajectory, and the two black rectangles represent two mirrors. Here we can see that the two mirrors see the straight line trajectory of the light ray with the speed c. C is light speed. It equals to 3 times 10 to the power of 8 meters per second. Okay, here we can see that this kind of pattern constructs a light clock, and we call it stationary light clock. This video shows a uniform moving light clock. A light clock moves with a constant velocity v towards the right side. Compared to the stationary light clock, the photon has to travel longer in each step, leaving one mirror and reaching the other mirror. So here we can say this kind of pattern can construct a light clock. Here in this figure, it shows that in a uniform moving light clock, the photon leaves the bottom mirror at the position B1 here, and then reach the top mirror at the position A2. A2 is here, and then reach the bottom mirror at the position B3. B3 is here. So the photon path is B1 to A2 and then to B3. And in this figure, we can see that the triangle B1, A1, A2 is a right triangle, and the B1, A1 equals C times delta T1, and A1, A2 equals V times delta T2, and B1, A2 equals C times delta T2. Delta T1 and delta T2 are the time intervals for the light ray or photon to travel between the two mirrors in the stationary and uniform moving frame, respectively, and c is light speed. In the triangle B1, A1, A2, we know A1, A2 equals V times delta T2, and B1, A1 equals C times delta T1, and B1, A2 equals C times delta T2. And according to Pythagorean Theorem, we have the equation 4 here. A1, A2 squared plus B1, A1 squared equals B1, A2 squared. And we plug equation 1, 2, and 3 into the equation 4, then we have the equation 5 here. V times delta T2 squared plus C times delta T1 squared equals C times delta T2 squared. And from the equation 5, we can derive the relationship between delta T1 and delta T2. And this relationship is shown in the equation 6 here. Equation 6 shows the phenomena of time dilation. Delta T2 equals delta T1 over the square root of 1 minus V squared over C squared. In the triangle A1, B1, A2, regarding the angle, this angle A1, B1, A2, we have sine angle A1, B1, A2 equals V over C, and the cosine the angle A1, B1, A2 equals the square root of 1 minus V squared over C squared. And in the uniform moving frame, the light ray speed can be decomposed into two components. The horizontal component, V light ray horizontal, and the vertical component, V light ray vertical. The first point here is the horizontal component of the light ray speed is equal to c times sine the angle A1, B1, A2 equal V. This is same as the mirror speed. We note that the horizontal component of the light ray speed is equal to the mirror speed in the horizontal direction. And the second point is the vertical component of the light ray speed is equal to c times cosine the angle A1, B1, A2 equals c times the square root of 1 minus V squared over c squared. And we note that mirrors do not move vertically in a uniform moving frame. So based on point 1 and point 2, we know that in a uniform moving frame, the mirror see the light ray bounces up and down with the speed c times the square root of 1 minus V squared over c squared. This leads to time dilation. The video A is the video we just showed. It is a uniform moving light clock. In video B, it shows that in a uniform moving frame, the two mirrors see the straight line trajectory of the light ray with the speed equal to c times the square root of 1 minus V squared over c squared. In stationary frame, this speed is equal to c. In uniform moving frame here, this speed is reduced to c times the square root of 1 minus V squared over c squared. This is smaller than c. So this inequality causes time dilation in the uniform moving frame. This slide summarizes the similarity and the difference between the stationary light clock and the uniform moving light clock. The similarity is that the mirror sees the straight line trajectory of the light ray, and the difference is on the speed of the light ray with respect to the mirrors. In the stationary frame, the speed of the light ray with respect to the mirrors is equal to c, and in the uniform moving frame, the speed of the light ray with respect to the mirror is equal to c times the square root of 1 minus V squared over c squared. This slide is about another kind of light clock. It is called spinning light clock, and more specifically, we call it A-type spinning light clock. The two mirrors rotate around a common point. It's called center. The center is here, and the two mirrors and the distance between the center and the two mirrors are same. In video A, it shows a photon marked by the green colored disk and the light trajectory marked by the blue line and the mirrors marked by the black color blocks. In video B, it shows photon and mirror, but it does not show the light trajectory marked by the blue line in video A. In video C, it shows the two mirrors see the curved trajectory of the light ray that leave one of them and reach the other. So in video C, it shows that light banding appear in the spinning frame. Here it shows another kind of spinning light clock. It is called B-type spinning light clock. The two mirrors rotate around a common point. It's called center. The center is here, and the distances between the center and the two mirrors are not same. They are different. One mirror moves along this circular trajectory, and the other mirror moves along another circular trajectory. In video A, it shows photon marked by the green color disk and the light trajectory marked by the blue line and mirrors marked by the black color. In video B, it shows photon and mirror, but it does not show the light trajectory marked by the blue line in the video A. In video C, it shows the two mirrors see the curved trajectory of the light ray that leave one of the two mirrors and reach the other. Uh, Here we talk about what the two measures see in the spinning frames with different angular velocities. Here we have 4 different angular velocities: omega 1, omega 2, omega 3, and omega 4. Omega 1 is smaller than omega 2. Omega 2 is smaller than omega 3, and omega 3 is smaller than omega 4. What we observe is that as the angular velocity changes, the shape of the light ray seen by measures change accordingly. Here, what we want to address is that as the angular velocity increases, the trajectory of the light ray in the spinning frames appears more and more curved. Here we want to note that in the spinning frames, the speed of the light ray is time varying. It is not a constant. In this slide, we show how time contraction happened in the A-type spinning light clock. Geometrically, we can see that the distance between B1 and A2 is smaller than the distance between B1 and A1. B1, A2 is the path for the photon in the spinning frame, and B1, A1 is the path in the stationary frame. So the photon travels shorter in the spinning frame. So time contraction happened in the spinning frame. Now we do it algebraically. The radius of the circle is denoted as r. So this circle has a radius r, and we have the equation 1 here. 2r equals c times delta t1. Delta t1 is the time interval for the light ray to travel from one mirror to the other mirror in the stationary frame, and c is the light speed. And in the triangle B1A20, this triangle B1A20, according to cosine law, we have the equation 2 here. B1A2 squared equals OA2 squared plus OB1 squared minus 2 times OA2 times OB1 times cosine angle A2OB1. And we know that this angle A2OB1 equals pi minus this angle A2OA1, and this angle A2OA1 equals omega times delta T2. And we also know that B1A2 equals C times delta T2. B1A2 equals C times delta T2. It is the path of the photon in the spinning frame, and OA2 equals OB1 equals R. OA2 equals OB1 equals R equals half times C times delta T1. And we plug equations 3 and 4 into the equation 2, and then we have the relationship between delta T2 and delta T1, and this relationship is shown in the equation 5 here. This slide talks about how time contraction happens in the B-type spinning light clock. Similarly, as the A-type, we can see from the geometric aspect that the distance between the point B1 and A2 is smaller than the distance between B1 and A1. B1, A2 is the path for the photon to travel from one mirror to the other mirror in the spinning frame. So in spinning frame, the photon travels shorter, and this results in the time contraction. And now we do it algebraically. In this case, the distance between the center and the two mirrors are not the same, they are different. And we denote the ratio of these two distances at k. K is equal to R1 over R2. R1 is equal to OA1, and R2 is equal to OB1. And we know that R1 plus R2 equals C times delta T1. Delta T1 is the time interval in the stationary frame. And we know K is not equal to 1 here. If K is equal to 1, it reduces to the A-type spinning light clock, not the B-type here. In the triangle B1A2O, B1A2O is triangle. According to cosine law, we have the equation 3. B1A2 squared equals B1O squared plus A2O squared minus 2 times B1O times A2O times the cosine the angle A2OB1. This angle A2OB1. And we also know that B1A2 is equal to C times delta T2. You can see here the photon traveled from B1 to A2 in the spinning frame. So B1A2 is equal to C times delta T2. And this angle A2OB1 is equal to pi minus A1OA2. And this angle A1OA2 is equal to omega times delta T2. Delta T2 is the time interval in the spinning frame for the photon to travel from one mirror to the other mirror. And we can also calculate the R2 and R1 by combining the equation 1 and 2. And we have the result here. The R2 equals 1 over K plus 1 times C times delta T1. And R1 equals K over K plus 1 times C times delta T1. And then we plug the equation 4 to 7 into the equation 3. Then we have the relationship between the delta T2 and delta T1. And this relationship is shown in the equation 8. Here we put 4 different light clocks together, and we can see that we can have different ways to construct different kinds of light clocks. Stationary light clock, uniform moving light clock, and spinning light clocks. Here we summarize the main content of this paper. The first point is how spinning light clocks work has been demonstrated. And the second point is it is possible for clocks to tick more quickly in non-inertial frame, such as spinning frames. And the third point is ergodicity is right. Time may go more quickly or more slowly in moving frames. Thank you.